You just allocated a massive budget for a custom CNC machined part. The 3D coordinate inspection shows perfect dimensional accuracy. But when it arrives, the surface is covered in cold, raw machine marks. Make no mistake, these micro-topographical flaws aren't just cosmetic blemishes. They are structural ticking time bombs. These microscopic peaks and valleys trap moisture, trigger galvanic corrosion, and act as stress concentration points that dramatically accelerate fatigue failure. Today, we're going to discuss the reason for conducting surface treatment, various surface treatment processes for CNC processed parts, and how to choose the appropriate surface treatment method. Fresh off the mill, bare metal is highly vulnerable. Surface engineering serves three fundamental industrial purposes. Passivation and corrosion mitigation. It seals the substrate from environmental electrolytes, halting electrochemical oxidation in its tracks. Functional enhancement. It modifies surface roughness, lowers the coefficient of friction, prevents galling, or provides specific properties like electrical insulation or medical-grade biocompatibility. CMF and brand identity. It achieves precise color, material, and finish, CMF, specifications, meeting rigorous industrial aesthetics or tactical camouflage standards. Our first category is mechanical finishing, where we use physical kinetic energy. The industry benchmark is bead blasting. By bombarding the substrate with spherical glass or ceramic media under compressed air, we obliterate directional tool marks, creating an isotropic, diffuse matte texture. Pro engineering tip. Bead blasting alters material thickness at a micron level. For high-precision bearing bores or critical threads, rigorous masking is mandatory to prevent geometric dimensioning and tolerancing, GD&T, failures. Next comes mirror polishing. By systematically reducing abrasive grit down to sub-micron levels, we achieve Ra less than 0.1 micrometers. This finish is essential for medical tools and vacuum semiconductor components, where even microscopic crevices can trap contaminants, risking bacterial growth or outgassing. The second family is chemical and electrochemical conversion, where we leverage material science. For aluminum, anodizing is the gold standard. Type 2 anodizing generates a porous aluminum oxide layer that excels at absorbing organic or inorganic dyes for stunning aesthetic colors. Conversely, Type 3 hardcoat anodizing is built for performance. With a dense film exceeding 50 micrometers and hardness up to 600 HV, it provides exceptional wear protection, making it the go-to choice for sliding mechanisms and high-friction assemblies. For stainless steel, passivation is non-negotiable. Submerging parts in nitric or citric acid strips away free surface iron contaminants introduced during machining, spontaneously forming an ultra-thin, chromium-rich passive oxide layer that eliminates localized pitting. If you need robust corrosion protection but your application demands low contact resistance for grounding or electromagnetic interference, EMI, shielding, bypass anodizing, which is an insulator, and specify a chemical conversion coating, often referred to as Alodine or chromate film. The third family is coatings and plating, which introduces a secondary material to the substrate. Powder coating applies electrostatically charged polymer powder that is cross-linked in a curing oven at 200 degrees Celsius. This yields a thick, highly ductile skin with elite impact resistance, perfect for structural frames and industrial enclosures. For highly complex internal geometries and blind bores, electroless nickel plating is an engineer's secret weapon, driven by a self-catalytic chemical reaction rather than an electrical current. For highly complex internal geometries and blind bores, electroless nickel plating is an engineer's secret weapon, driven by a self-catalytic chemical reaction rather than an electrical current. It deposits a perfectly uniform nickel-phosphorus alloy across all surfaces, completely free from line-of-sight limitations. So, how do you select the optimal process? Don't guess. Base your decision on functional requirements. We have synthesized this engineering decision matrix for your next design review. Selecting the right surface finish is not just a final touch, it is a core design variable that dictates your product's lifecycle. Balancing dimensional tolerances, cost, and environmental survivability requires deep supply chain integration. At KAIAO, we provide end-to-end manufacturing solutions, seamlessly bridging the gap between precision CNC machining and advanced surface engineering. From rigorous hard coating to aerospace-grade passivation, we deliver components optimized for performance and built for survival. Hit the like button, subscribe for more deep dives into material science, and leave your manufacturing questions in the comments below. We'll see you in the next video.